Okay, so then we can start. Welcome everybody once more. It's official IAU G2 online conference series. You know, this is about massive star, and today is my pleasure to introduce Berto Castro, who will be delivering the 10th seminar already. And let me first say a few words about his career. So he started here in the Canaries, making the PhD under the supervision of Artemio Herrero on spectroscopic studies of extragalactic massive stars and basically mostly blue massive stars. And this has been the main focus of the rest of his career. I've seen when I was checking his CV that he's moved a lot. You've moved a lot, Berto. So he was in the National Observatory of Athens, working with Alquisti-Bonanos. Then he moved to Germany to work with Norbert Langer in the Arlander Institute for Astronomy. Then he went to Michigan to work with Sally OA, and then came back to Europe to work with Martin Roth in the Leibniz Institute for Astrophysics. And in a few months or 1 month ago, he started a new position in the University of Göttingen. So it's one of the situations in which as the evaluation panel called international, how it's called in English, internationality is obvious. Okay, so he's, as I say, he's expert on quantitative spectroscopy of blue massive stars. And he has been also a PI or co-investigator or several observing proposals, mostly with a large telescope, with like SALT, Gran Telescopio Canarias, VLT, Magellan. And recently he's been working in things related to the MUSE and the Blue MUSE instruments. And also he has started to be a co-leader of one of the sub-surveys of for MUSE to get data soon for galactic orbit type stars in the southern galactic plane. And I think this is all I say. So thank you very much, Berto, for accepting our invitation. And as I say, it's a really real pleasure to listen what you want to tell us.
Thank you very much for the invitation. Hello to everybody. I just only wanted to say that you have any question, you can interrupt me. In the way that I'm sharing the screen, I don't see you. So if you raise your hands, I'm not going to see you. So just stop me. So today I would like to give you a brief tour about integral field spectroscopy, focusing resolved stellar population and more specifically in massive stars. I will basically focus most of the talk in 30 Doradus and some of the nearby galaxies where we have developed our work, but I would like to give you a brief summary of other projects. Let me start saying that our main goal, I guess, for many of you too, is to understand a bit better how is the stellar evolution. During all these many years, so many studies has creating a more clear picture about that here, for example, in the Hercules-Russell diagram, how the stars evolve, how the different phases that they are going through along their life. And it's clear that the initial mass is the starting point for all of these stories. But when we go to the most massive stars, it's not the only parameters. So there are other factors that are going to affect the evolution, for how long they live, how much radiation they are going to emit. And this clear is important not only for understanding the stars in themselves, but also to extrapolate it to understand star-forming galaxies far away where we are not going to be able to resolve the stellar population. As I told you, the initial mass is clear the starting point, but also we have the point of the metallicity is also going to affect how long the stars are going to live, for how long they are going to be in the main sequence. Not just only the metallicity, but also how is the interpretation in the interiors of the star. For example, here comparing two different stellar tracks where they use different overshooting parameters. You see how the extension of the main sequence change. So we need more data to constrain all of these parameters. Of course, duplicity is going to play a huge role in stellar evolution, and we know that once the star is starting to interact between each other, the evolutionary tracks change. The life of them are also drastically follow a different path, and that's of course something that we also need to have in mind to understand better how the life of these stars is. A more exotic tracks here, when you play with magnetic fields, it can also have an important impact in the evolution of the star. Here is, for example, also when we play with the low metallicity and fast rotation, we create these chemical evolutionary tracks, where you see that instead of the star evolving to the lower temperatures, they are moving to the high temperatures. And again, that is going to have an important impact regarding to the radiation that these stars are going to emit to the interstellar medium, and how they are going to interact with the inside of the galaxies. So how do we try to understand all of these parameters? How we can try to constrain all of these effects? Having more data, it's key in this story. Be able to track, place all of in the Hercules diagram, give us a hint of how is the evolution of massive stars, so can use to constrain stellar evolution. Here is maybe a more complicated plot where I mixed data from the SMC, studies from the Milky Way, and you see that we starting to have already constraints that we can use to anchor or to try to determine better the evolution of these stars. For example, how is the role of the metallicity in the beginning of their lives? How is we can explore the Hercules-Russell gap, try to determine some empirical terminal age main sequence that we can use later to constrain the overshooting parameters in the model. We can also go to the most massive stars, and based on the observation, try to impose a mass, how the most massive stars could be. We can explore the inflation of the envelopes of the stars, or the role of the stellar winds in the evolution of this object. Or going to the most massive stars close to the main sequence, we also discover this lack of the stars close to the sun. So these are also points that could introduce new factors for understand better the evolution of these stars. So let me put you a more clear diagram here. So just to summarizing, one of the key factors to understand is having data, having a lot of data at different stellar evolutions, at different phases, to create these stellar archaeological maps that we can use to constrain the evolution of the stars. Data is not, of course, is not the only parameter in this story. We also need a robust quantitative analysis. We need accurate stellar atmosphere model. We need a accurate atomic model so we can reproduce the transitions. But in this talk, I'm going to be a bit more biased to the gathering of the data. So don't be upset to the people that are working in the atomic models and stellar atmosphere models. This is, for example, a slide that I borrowed for Sergio some years ago. Maybe these days he has a more updated one to show the effort of many groups to creating and gathering data, gathering high resolution with high signal to noise in the Milky Way. There are several projects running in the northern hemisphere, like it was Jacobs, the GOES North, even MINES, that it was original, obviously designed for the studying magnetic fields, but they also create a large sample of stars that we can use to many other studies. In the south, we also have Formos. Well, in the north, we have WIPS that's going to start producing data soon, and other surveys. Yes, this is only in the Milky Way, but obviously also in the large Magellanic Clouds, they are going on, and there were also important surveys focusing in the gathering data and trying to understand statistically better the evolution of the massive stars. I would like to show you a few slides of the Formos, because it's the one that I'm currently involved more. For example, the 1001 Magellanic Field Source Survey, where it's also dedicated a part of the time to the massive star population. And we are going to gather several thousand of OB stars in the large Magellanic Cloud and also in the small Magellanic Cloud. We also are running a survey in the Milky Way as part of Formos, where we are targeting more than 19,000 stars that we are hoping to also to get a nice picture of the stellar population of the massive stars in the Milky Way. And indeed, this multi-object spectrographers are going to provide a huge amount of data, which is going to be incredibly useful to create these maps, archaeological maps, and constrain the stellar evolution. But we have several limitations when we are doing observation with these kinds of instruments. Massive stars are formed in very crowded areas. So sometimes, like in the case of 30 Dorados, that here in the picture, it's not easy if we wanted to map the stellar content in the core of the cluster with the most massive stars here. There was nice work from the Flame survey, but still the core of the cluster was not very well mapped. And here is where the integral field spectroscopy has shown a huge revolution, I would say, to map these very crowded areas, to getting data for all the single pixels that you see in the image. Here it was it's a MUSE composition of 2x2 pointings, and we have information for all of the stars. Before going on with MUSE, I would like to just to show that the integral field spectroscopy focusing on stellar population is a story that has been way before MUSE was commissioning in 2014. Several projects starting probably earlier than PMAS, for example, or the Argus in Flames, were showing the capabilities of this technology to explore and extract data for resolved stars in different areas. But of course, was the commissioning of MUSE and the large field of view that has been a huge revolution for the resolved stellar population and the spectroscopic analysis of massive stars in very crowded areas. Yes, I also wanted to show you a brief plot from the paper that Martin Roth just published in 2014 this year, showing the impact of MUSE in the publication that probably many of you are aware when you apply for time and you see how the pressure of MUSE is right now. You see how it's right now is the most successful in publications instrument of the VLT. And also he split all of this publication in the different areas and found out that the resolved stellar population and the Milky Way is starting to be also a large fraction of this work, even if the instrument was mostly originally focused or designed for cosmology. The role of the stellar population with the integral field spectroscopy is really catching up with the community. And this is, for example, a few examples of work that they have been doing in clusters using MUSE and showing the incredible capabilities of the instruments. In NGC 3603 in the Milky Way, there's a very massive a very massive cluster that is not very clear here, but they are strong emission of helium-2 here in the core. So it's kind of interesting to see how you can disentangle that with MUSE. Also, the supernova remnants close to the core of 30 Dor. There is this red spot here, or the several clusters that Kaman et al. Have been studied in the Milky Way and the Large Magellanic Cloud. Also in the SMC, this nice work by Bodensteiner in NGC 330, where you see that the population of emission stars are really popping up in this color image of the MUSE pointing. Other two, this is an example of other two clusters also in the SMC that is showing the incredible resolution of the instrument to resolve stars and create it and do spectroscopic studies for all of the individual objects that you see there in the image. But I would like to go back to 30 Dorados because it's where we have been doing our work. So I will also like to show you all the capabilities using this data set as an example. As I told you before, this is data from the commissioning time from 2014 with 2x2 pointings. And they were enough to basically map the entire core of the cluster. They were not obtained with the best seeing conditions, but even though it was good enough to really explore the spectra of all of these stars. This is, for example, an aperture extraction of this blue supergiant. Here you have the data and the best fast-wing model that we managed to get for this one. If you are not familiar with MUSE, you maybe will notice that we are basically focusing in the red side. It's not for the massive stars. It's not probably the best range in the optical range. We will have preferred a bit bluer when they are more metallic lines, a more Balmer transition that we can use to constrain temperature and gravity, for example, silicon 3 and silicon 4. But even though we have quite some pretty much information about helium-1, helium-2 transitions, we still have some Balmer H-beta and H-alpha and all the Paschen lines that we can use to constrain effective temperatures and gravity. For this study in 30 Dor, we basically, for these pointings, we extract like 2,200 sources. We study the kinematic of them, getting an average velocity of 271, compatible with the previous study. And for that study, for that catalog, we model 333 stars, those with signal to noise higher than 50. For this work, we find basically this is the distribution of all of these stars in the spectroscopic Hertzsprung-Russell diagram. We find two groups with ages between 2.1 and 6.2, and another strange group away from the main sequence that we assume that is emission stars that are probably have some issues during the modeling. This is also a issue that we found in the analysis of a sample in the Epson C in 2018, where we were sure that there were BE stars. So here, finding the same result, we adopted that the position of this star is also because of some problem in the modeling of this object. But MUSE can give you the option to go a bit further. It's not just only extracting and do a statistic with all of the stars, but we can also explore individual interesting targets like this Wolf-Rayet Melnik 34. And even if the sync conditions were not good, it's still interesting to try to explore how is the extension of this star and how is the impact of such a very massive star in the ISM. And this is something that MUSE allows. And I will go a bit further later with better quality data, and will show you how we can do it a bit more of the exploration of the role of the star in the ice scene. It's not only the stars. We have all the spectroscopic information for all of the pixels, so we can basically switch, focus in the ISMs and explore how is the kinematic and the distribution of the gas around the massive stars. This is something that we do in 2018. We explore the intensity map of H alpha, also the kinematic of the gas, finding how the gas is moving blueward respect to the core of the cluster in the part of the huge bow shock that you see in the front of the cluster, and redshift in the other part. We also explore the broadening of the line. With MUSE, we know that we have a lower resolution. We have a resolution around 3000 around H alpha. But even with this poor resolution and studying the broadening, we can have an idea where the parts where we expecting to have a composition of different clouds moving at different velocities. We explore also extinction based on H alpha and H beta. Effective electronic temperature, which is a bit more tricky because some of the transition using in this are very faint, like the nitrogen 3. And we also study the electronic density, which reveals to very useful to find spots where maybe star formation are happening, like some of the ones already detected by Wolfram et al. And this is something that it was already nicely explored in the Pillars of the Creation by Anna McLeod. And here we did a similar work in the 30 Dorados, finding targets for subsequent follow-ups and see if we can go deeper in what is behind of them. But even if the capabilities of MUSE was amazing for disentangle all of the stars, even as I said, with a sync of 1 arc second, the core of the cluster is still not resolved by MUSE. This changed in 2018 with the commissioning of the narrow field mode, and that was allow us to go even deeper in the study of 30 doors using integral field spectroscopy. With the MUSE narrow field mode, obviously the field of view was reduced significantly to 7.5 per 7.5 arc second, but it gave us amazing spatial resolution of the core, reaching the same that the Hubble Space Telescope. Here it's an example of 9 pointings that we took in the core and around of the most massive Wolf-Rayet stars. And as soon in the core of the cluster, you can I hope you can see more or less how the MUSE narrow field mode was able to resolve R136A1, 2, and 3. In total, we have so far extracted more than 18 sources, more than 1,000 with signal to noise higher than 10, and we are working in the stellar modeling and the clustering and the gas kinematic of all of these fields. This is an example of some of the stars extracted by these cubes in the narrow field mode. Only I just cut it here. I just only show you the blue part of the spectrum to show you that it's still a very good signal to noise for some of them, finding perfectly well the helium-2 and helium-1 that is going to be basically our criteria for the effective temperature. And also this Wolf-Rayet, that is the crazy one, this carbon Wolf-Rayet carbon star. This is a very preliminary work, so we have to be cautious, but I would like to show you, because here on the left is the same plot, the same result that I showed you before with using the wide field mode, where we find it's not clear because here it's not the density like in the previous one, but here we find 2 different edges plus this bunch of stars that we claim, but we assume that there are emission stars that are not very well modeled based on in this other previous study. In the narrow field mode, focus only in the core of the cluster, we find so far, this is something that we need to recheck again, a more coeval and younger population of stars. We didn't find any object that could be claimed as a emission star poorly placed by the modeling. And we also find that stars closer to the main sequence here, to the 0A main sequence for the high massive stars. This was one of the problems that we find in the wide field mode, that there was some kind of gap that we didn't find younger stars here, and we thought that maybe it's a problem, or maybe the younger stars are in the core of the cluster. If we can confirm that, it looks like yes, the core of the cluster can populate it a bit closer to the sun. I didn't speak about duplicity of binary with MUSE so far, but because the resolution is not probably the ideal one to go to monitor and getting more data from the binary. But even though if the resolution is 3000, is it possible to disentangle and to study variability? This is, for example, a string case where a closed binary with a very high velocity, radial velocity between two components, and in 3 epochs we were able to disentangle both. But the good point is that it's possible to study variability and duplicity in the core of the galaxy and core of the cluster using MUSE. We also are working in the ISM with the narrow field mode. This is basically a nice picture of using oxygen 3 H alpha and sulfur 2, labeling all of the warm jet around the cluster. And we are working also to explore, as we did with the wide field mode, extinction, temperature, and density. And I would like just go briefly, because before I told you that it was possible to explore a bit more how is the role of the most massive stars in the ISM, and I pointed out to Melnik 34. In the wide field mode, we were limited by the resolution, but now with the narrow field mode, we were able to try to explore much better how was the impact of these very massive stars in the ISM, and we found an apparent outflow of material coming out from the jet from this binary system using H alpha. And exploring a bit further away the ISM, we found that the nitrogen 2 also present a filament that is basically following the same direction that this H alpha outflow were pointing out. So this is something that we would like to also to explore in order of the warm jets in the system, to try to find similar outflow of material coming from these stars. We also have explored using MUSE as a template to further galaxies. We have the opportunity to integrate all the lights coming from these cubes of data, so we can compare how is the integrated light with other star-forming galaxies where it's not possible to resolve the stars. So this is a plot of the integrated lights of the 30 door, where you can see that the known bumps in the blue due to the warm jets, and also in the carbon are present. So we create some templates for exploring further galaxies. But now I would like to go a bit further away to 30 Dorados to show you how the resolved stellar population with this technology is also very useful even if in further galaxies. This is an example of a work that was just published also this year in I6 1613. Although it was not focused for the massive stars, they designed 3 fields to study the kinematic of the stars, so the nicer bubbles of the most massive star were not included. But I would like to show you, because basically proof that that is possible to get very high signal to noise with enough information to modeling and constrain the parameters of all the stars and the kinematic. Leo P was another case where we have been exploring for massive stars. This is a irregular galaxy, a dwarf galaxy with a very low metallicity. So one of the key points of Leo P was to explore the role of the metallicity in the massive star. We were able only to classify a bunch of OB stars. We didn't provide analysis for this because the signal to noise was not high enough. Although we were able to detect them. All the blue stars here are the massive stars that we found in Evans et al. 2018. We also find some carbon stars. And exploring the H alpha also revealed the activity of the stellar activity that it was passing. Basically, nobody has noticed before in the galaxy. Just to show you, because if you see the galaxy Leo P in the optical range, this is from the HST, you don't really see all the formation and all the bubbles that H alpha mapping by MUSE revealed. And we can even go further to NGC 300 and trying to get also resolve a population for all of the star formation in this galaxy. This was one of the original projects of MUSE, led by Martin Roth, where he designed exploring like 7 fields to also to prove the capabilities of the instrument to resolve stars at a distance of NGC 300. I would like to give you a zoom in these are the 3 inner fields where we got data with a very high image quality, enough to resolve the stellar components, and some of the most massive some massive stars are still here, and also the ISM that it has been explored in Micheva et al. 2022, where he studied the H2 regions and diffuse gas of all these fields. We are currently working in progress in this galaxy to the modeling of the stars. This is a work that we're hoping to be published this year. Here is also an example that despite of the distance and the signal to noise, the information in the spectra is good enough to constrain temperature and gravity, basically on the Balmer lines and the helium-1 and helium-2 transitions. But even if still MUSE has a lot to give, a lot to explore, we are already thinking in the next step. So Blue MUSE is already accepted for the next generation of the instruments of BLT and is currently in phase A. And for this instrument, massive stars become one of the key drivers of the instrument. Now we are talking about having an instrument similar to MUSE with a higher, in the designs, we are hoping that it's going to be higher spectral resolution, but covering the blue range. In this example, for example, red MUSE is basically covering between 4,700 until 10,000. Now Blue MUSE is hoping to be close to the Balmer jump until 5,500. So all of these transitions that we normally use when we do stellar atmospheric characterization will be available. A part of the chemical lines that will be great to do also chemical composition. So it's going to be also a revolution for the massive stars. If we go a bit further in time, hoping for something else, this is still a conceptual design that we just published in a white paper a few weeks ago, hoping but someday we will be able to have a 12-meter telescope dedicated only to spectroscopic surveys. And the idea is that it will be nicely equipped with a multi-object spectroscopy covering this external ring in high resolution and low resolution. And the inner part is the idea is to have integral field unit with a field of view of 3 × 3 minutes, which will be amazing to mosaicing large portion of the galaxy with that instrument. But of course, this is something that is still far, far, far away if it's happening in the future. And this is basically what I was going to share you about MUSE and resolved stellar population, hoping that if you were not aware of, you were aware to give you awareness of how great are the potential of the instrument for the massive stars community. Thank you.
Okay, thank you very much, Berto, for this very nice talk. It's nice to see after the last talk have been more on models. So going back to observation is always nice. And it's great to see how we are getting more and more data on the future prospects. And especially I like very much this blue MUSE. I think is going to be it's going to make a real difference in the way we obtain information. So now time for question. If anyone wants to ask Berto.
I'm going to stop to see you a bit better because I don't see you now.
No questions here. Sally?
Yeah, hi, Berto. Sorry, my video isn't working. Okay, I just turned this off. Very nice talk. I was just wondering about one of the things that you mentioned in passing. There was an object where you referred to an outflow from when looking at the gas, where you saw clearly a red shifted piece and a blue shifted piece. And
Yeah.
I was just wondering whether that object could instead be interpreted as a rotating annulus.
I don't think so, because what we found, it's a very sharp peaks in H alpha, moving away a different. It was not just only these two. There are several more. There are several more outflows. So, and they were also time dependent, because we have a second epochs and we saw that we're changing. I don't know what to say. I will say that I don't see it clearly, like we said, it was something rotated.
Okay, thank you.
Artemio?
Yeah, nice talk, Berto.
Thank you.
Two questions related to the HR diagram that you presented for, in which you presented the comparison of the wide field and the narrow field observations with MUSE. Can you show it just for,
yeah, let me see if I can share. I can see you at the same time. What are you seeing?
No, it's the waiting for the next generations. A little
but you see the presentation?
Yes.
We see the presentation, yeah.
Wait.
Exactly which slide this was?
In full screen?
Mm-hmm.
Now in full screen, yes.
Okay. Yeah.
That one, yeah. I have two questions. The first one relates to the gap. You said that, we can see that in the with a narrow field, the gap at least partially disappeared. So I could like to know what are the error bars in those temperatures. And the second question is whether you have any idea of what are the objects which are very blue extended, so it's are very massive and very blue.
Yeah, I have to repeat again. That was a very preliminary analysis. Okay, so let's have it like with a pinch of salt.
Yeah, we do.
Maybe then we will do it properly. Then everything going to shift everywhere. So the error bars, I cannot tell you right now. So maybe once we add the error bars, we discover that this is yeah, everything is compatible with the gap and nothing else there. So I was just curious to find out that some very young stars were populating where they're supposed to be. So
well, it's very interesting in any case.
Yeah,
so
because yes, I found also with Olgado results and also with the in 2014 when I gathered all of this data in the background image here, that we also find this missing group of stars there, and we were wondering if there was a bias or not. Yeah. So, and your second question is what are all of these very blue stars here? These are because this preliminary analysis that I am using, I was doing a combination of fast wind and power for the Wolf-Rayet. And these are basically all the Wolf-Rayet that are in the field, on some of them.
But you get temperatures in excess of 100,000 Kelvin.
Yeah.
Are these reliable? Yes.
Again, let's go one by one and check them before. I just only know that they are, let's say, exotic O stars.
Okay, keep us informed.
Yeah.
I also have a question related to these two diagrams. So can you explain again what is the difference between the wide field and the narrow field? So it's spatial resolution, no?
It's the difference is spatial resolution, but the main difference is that the narrow field mode is sampling the core of the cluster that the other one didn't. So they are.
So in wide field, basically you are not resolving all the stars that are to the right in blue.
Yeah.
Yeah. Okay. And do you have an image of where the two fields are? So I don't remember if you had it in your talk.
Yeah.
What is the location of the blue stars in the region?
No, I don't have one of them, but yes, I will build one for you.
Okay, just curiosity to see why.
Yeah.
Okay.
No, it might be some overlap between the both, which obviously is something that we will do to compare the results.
Because what I'm surprised is that you have so many objects in the
because you saw the image of the core that suddenly.
Yeah. Okay. So we can talk later.
No, but yeah, but it's something. Some of them must be in common. I haven't checked that. So the cross check is something obviously that we have to do.
Okay, Joe. We cannot hear you.
Sorry, yeah, I have just realized. So, Berto, thanks a lot for this very nice overview. I was particularly impressed on the quality of the spectra from this part which you called blue MUSE. Yeah, can you please go to this spectrum?
No, but yeah, I didn't say that. But this is not a real spectra. This is a simulation.
Okay.
It was.
Forget my question.
Yeah, it was to show you what is the range that blue MUSE is going to cover, and which are the lines that are going to be there for the massive stars that blue MUSE is going to cover. But no.
So is there any instrument which in the next years which will cover this wavelength range in such a quality?
Yeah, but stuck. I would say that maybe in 2030 we will have the instrument.
So is not X shooter providing something like that?
Yeah, but usually the quality is not so good, huh?
Okay.
Mm.
I was just interested. Actually, my question was a bit different, but now it's not so relevant. But anyhow, I mean, at some point we have to go into this range because it will become available. And then the question is whether there are already some investigations on the spectral features of these of this region, particularly whether there are some regions or might be some regions which have a sort of a atypical behavior, as we have it in the hot star region around 4,600 angstrom, where we had a lot of these pseudo emission lines and so on. So whether there is something similar for specific spectrotypes in this range. But okay, good. Since you don't have, since this was simulations, that's a different.
Yeah, no, not yet.
Good. So, but we have to go into this CLU anyhow.
But maybe with UBES, because UBES is reaching this region. So for the available data with UBES. Mhm.
Okay, thank you.
Any other question to Berto? So while people is thinking about more questions, maybe you can remind us what is the timeline for Blue MUSE? So what is the and where is
this is something that you have pressed in my head and I don't. So maybe 2030.
Okay, this is
maybe, yeah, it's in phase A. So still,
but it's
7
more
years,
closer
maybe.
to 10 years than 5.
Yeah.
Any other question? If not, then thank you very much again, Berto.
Thank you.
And hope to see many of you in our next seminars. So we close for a moment. Ciao.